So, all right, starting now. All right, before I forget, I wanted to mention that last week already. So as most of you will know, so the teaching evaluations are open, and so hopefully it's very important, right? So the college encourages all instructors to encourage you to complete the teaching evaluations. It's important feedback, so both for the college and also the instructor, right? And so in order to give you an extra incentive for completing the evaluation, so I was thinking a little bit, because I have already such a complicated system in place, right, with the grade improvement options. I will give you a grade, so basically bonus points for your final. I'm not 100% sure yet how many, so because I don't know exactly how many points the final will have, but I was thinking something like 2 points, 2 bonus points or something like that, and then if the overall number of points is similar to the midterm, which is very likely. So so small option for grade improvement there. So if you complete the teaching evaluation, so then you will get that.
Hello?
Yeah.
Did she freeze?
Can you?
There we go. There we go.
All right, super. So as I said, so there will be the so 2 bonus points for your final, right? I will also send an email to that you have that in writing, and yeah, so just as an additional incentive. And I'm not sure how long they are still open, but at some point they will close. So I also know that, so heard from some students, so it went in their spam folder, so the notification. So maybe you want to check so whether that happened to you too. What else did I want to say? Oh, right. So and of course, so you have to either, there are 2 options. I mean, I have to know, right, to give you, in order to give you the so the bonus, I have to know. Well, the system has a function that you can notify the instructor after completing your evaluation. You can use that function of the system, and I will get an automated email that tells me so the student has completed the evaluation, or you can also do it in an informal way and just send me an email. Right, but so one way or the other, I have to know. Otherwise, if you do it but decide not to tell me that you did the course evaluation, so then I won't be able to give you credit for it. All right. So then our plan for today. So now just Nasia. Also, apologize for the delay in grading. So I will do my best to get them to you, to get the grades for both so previous assignments by tomorrow night. So by the end of the day. All right, so that you know where you're standing right before the final and before the last assignment. Okay, and then for today and tomorrow, as I had announced in my email already, I thought it might be more beneficial to also in terms of the midterm, the final, sorry, so to cover the so the theoretical basis today and tomorrow, so what's left for ANOVA. And then have you do the R stuff on your own. So I have posted 2 tutorials already, so that cover most of the stuff that you need. There's also like some basic R stuff in the slides, so we will touch on that so briefly during the lectures as well. And so to give you all you need to complete the assignment. And I will also add another markdown file so for you, right? So and the tutorials, the R tutorials so are in the tutorials folder, right? So not in the lab not in the labs folder. So I included that in the email, right, in case you can't find it. And the data sets for the tutorials that the tutorials are based on are also on Blackboard. So you can download those data files if you want to basically do it yourself so go over the examples yourself. All right. So I just wanted to add a few things to the one-way ANOVA. I mean, that is true for all ANOVAs, not only for the one-way so ANOVA. So we can use the power analysis function that we're already familiar with from doing regression, multiple regression. So we use the library PWR, All right, so this is power package. And then we are using the function pwr.ANOVA.test, and we have to specify the number of levels, right? That it's a k argument in our function. So how many levels do we have, or how many groups, right? So in case it's a factorial ANOVA where you have more than one factor, right? So you might have one factor with 2 levels, so 2 groups, 2 conditions, and another factor that has 3 conditions, 3 levels, and you have 6 groups total, right? So 2 by 3, and then your k would be 6, right? Okay, so then you have to, so what you have to know in order to determine the sample size to detect a certain effect of a certain size with a certain power, right? So power is 1 minus beta, just as a reminder. So it's the, so 1 minus type 2 error rate. So you have to basically define, so the power as f, right? So I gave you earlier this convention how you can calculate so the effect size if you have, right? If we have it in a different metric, so either as r squared or as r, so let's say all related, right? It's more or less the same coefficient, just expressed in a different way, right? A little bit modified or transformed. It's all this explained variance family, right? So the r squared, f, omega, and eta squared, etc., etc. All right, so but this function wants f, no? Not f squared, f. And so then you tell the function what your desired power is and what's the your type 1 error rate is, right? So what you set it, what you set your type 1, so you allow type 1 error rate to, in this case, 5%. And then so it will calculate so the required sample size for you in this case, so it would be 53 subjects, right? And that means we need that many subjects in each group, right? If you have an ANOVA with 6 groups, so that would be a pretty big sample, right? In this case, it's only 3 groups, so that's still a big sample, right? Still 159 participants in this case, or subjects, depending on what you're working with. All right. Alrighty, so last time, so in class, we were talking about the results of our overall ANOVA analysis, and we have learned that if we get a significant result, right? So if our f-test gives us a significant result, so then all we know is that there is, so that's a model most likely explains some variance in the population. That means that that at least, in most cases, at least 2 groups differ from each other, or to be more precise, so linear combination of the groups is not equal 0. So just fine lines, right? So so you can, as a rule of thumb, you can recall that if you have an overall significant ANOVAs and significant omnibus test, your f-test statistic for your overall ANOVA is significant, then it typically means that at least 2 groups differ. So 2 conditions are significantly different from each other. So that doesn't tell you, however, which groups actually differ from each other. So which groups exactly. And that is what you often are interested in, right? So if you, for example, testing a bunch of new treatments and you're comparing that to some baseline conditions, so either an established treatment or no treatment at all, so then you may not only want to know that there's some difference, so either between one of the treatments and your baseline condition, or I don't know, so maybe so 2 of the treatments are different from each other. You typically want to know what condition actually differs from what other condition. So you want, for example, know, is one treatment better than the other? Are both better than the baseline? So and you can tell from your overall ANOVA. So what you need to do is you have to do some follow-up tests to find out where the differences actually lie. And so there are different options to do that. The first one could be, right, we're doing multiple t-tests. But so we have talked about that 2 weeks ago, that this is a really bad idea in general, right? So, I mean, there is at least one statistician who has suggested to do that. So just to run multiple t-tests after a significant overall ANOVA. We'll talk about that in a few minutes. But so it's in general, it's a bad idea, especially if more than 3 comparisons that you want to make. So it's almost definite in those cases that you will deal with an inflation of your type 1 error rate. So your family-wise error, so the probability that you make a mistake in at least one of these comparisons will increase exponentially with the number of individual comparisons that you're conducting after. So basically the group pairwise group comparisons that you're conducting after you get your significant ANOVA result. So that is generally not a good idea. Another option is that you define so-called planned contrasts. So that means, and ideally they're orthogonal, so that means they're independent of each other. It's not necessary, you're not doing anything that's horribly wrong if you define non-orthogonals and non-independent, also called overlapping contrast. We'll talk about that when we're talking how to specify contrast as a differences. So you just have to keep in mind that so that they are non-independent, and that so that has certain implications also for the type 1 error rate inflation. And so because you're basically comparing overlapping chunks of variance over and over again. So it's not always a good idea, but sometimes you have to do it because your research question just requires it. All right, so what are planned contrasts? So planned contrasts are always hypothesis driven. So that means they're based on some theoretical assumption, and ideally based on pre-existing empirical evidence. So something that you know before you actually conducting your study, before you're starting your experiment, and they should be limited, right? So in their number. So you usually don't have a set of 10 really strong a priori hypotheses. So and the rule of thumb is it should be no more than 2 to 3. It's also important to keep in mind that if you have these specific expectations, so if you, for example, are only interested in, so not whether there's an overall difference in between your conditions, in the sense that any conditions differ, but if you're specifically interested in comparing so a limited number of conditions in your analysis, there is no reason to actually even look at the omnibus ANOVA findings, right? So you don't have to run your overall ANOVA. You can just limit yourself to really only looking at these specified contrasts, right? And that will also help you to keep your type 1 error rate low, right? So your overall, your family-wise type error rate. And I want to mention it here so that I don't forget it later, because you will find conflicting information in different sources. So many people say, if you're doing those, if you have those a priori hypotheses, right, and they're limited in numbers, they're based on theory and based on existing empirical evidence. So then it's actually okay to do these comparisons without doing any additional adjustments from multiple testing. So that means you don't have to adjust your P level, right? So what is a requirement for post hoc tests normally. However, more and more, so editors and in general the field is requiring it, even for the plan comparisons. So whenever you run more than one test with the same data set, right? So same data set, more than one test, then more and more, so you will be asked to correct for multiple comparisons. And so keep in mind, it's a very important point. So since the ANOVA is nothing but a linear model, so it's nothing but a regression model, So the same is true for testing your individual predictors in a regression analysis, right? So if you have a multiple regression analysis and you have 3 predictors, if you're testing the significance of your predictors, so if you basically, right, it's your t-test or your f-test for so significant improvement in the r squared. So then, so it might be appropriate to correct for multiple comparisons as well. So I'm a bit on the fence when it comes to these corrections. I think, so my opinion is, I mean, I'm not a statistician, but so my opinion, and based on the literature, so if you have really strong hypotheses, so that are based on a solid foundation of pre-existing research, then I think having 2 to 3 hypotheses and testing them without adjusting your error, so your type on error, or your p level, so your critical values is okay. However, yeah, so you might find out during your career that so many people find that is not okay, right? And that you always have to do the corrections. All right. So a special kind of orthogonal contrast is called polynomial contrast, so also trend analysis, which can be applied if your dependent variable is equidistant, so basically on more or less on an interval scale. So then you can test for certain linear, quadratic, cubic, etc. trends. So in the dependent variable across your conditions of your experiment. I'll talk about that in a bit. So if you do not have any specific strong hypothesis, right? If you're running your analysis and you get your significant omnibus ANOVA, and so now you're interested in finding out, so where the differences actually lie. So what conditions, what groups actually differ from each other. So then you perform what is called a post hoc test. And those post hoc tests require, so definitely there's no question about, they always require so basically an adjustment for type 1 error inflation. And there are different methods how to do that. We will go over so a few permanent examples. And so I basically here it says compare all pairs of means. So actually do not have to compare all pairs of means. So many software packages, if you don't specify anything else, it will automatically provide a comparison for all pairs of means. But keep in mind, so the more means you're comparing in general, so for many of these procedures, this means the more conservative your test will be. So the more stringent your so as an adjustment of your p level or the correction, right? So the harder it is for you, so the more power you are losing, right? So the harder it is to detect differences between conditions, so where they might exist. So, right, nobody forces you to do all comparisons. You choose, right? So you can say, I'm only interested in comparing those groups. I'm not interested in all. And so that is also an important criterion for choosing the right method to do the post hoc adjustments. Okay, so let's talk about the planned contrast first. So the basic idea is, so when we are doing these a priori or defining the a priori contrast, is that we are so we're further dividing the variability in our dependent variable that is explained by our model, right? So our sum of squares, so our model sum of squares, right? So the variance that can be that is accounted for by belonging to the different experimental groups. So we further subdivide that model variability. So if we break it down to test so which groups actually might differ from each other. And so again, it's very important that the way we are breaking down the variance, so the model variance aligns with the hypothesis that we have made a priori, right? Not after we have seen the results, but a priori before we actually started collecting the data. All right, so And if possible, I mentioned that, so these contrasts should be independent. Yeah, so they should contain, they should not contain, sorry, shared information. Yeah, so they should test unique hypotheses. So in what does it mean? What do I mean when I say they should not contain shared information? Yeah, I shouldn't do something like I compare group 1 to group 2, and then I compare group 1 to group 3. So then, so the comparison, right? The two comparisons contain overlapping pieces of information, so namely group 1, so it's completely identical. And so that is a problem because then they're correlated. So which make things a little bit more difficult. And also each contrast should only compare two chunks of variation, right? So you should take your model variation, so your model sum of squares, and you should divide it into two chunks, no more than that, two, right? And the reason is, yeah, if you would divide it in more than two chunks, if you would compare more than two chunks of variation, then you have the same problem as with the overall ANOVA. So we do no longer know where, so if you find a significant result, and we do no longer know where does the difference come from. So which conditions actually differ, or which chunks actually differ. Is it one versus the other two, or right? So that is not good, right? So that's always two chunks of. It doesn't have to be two single groups, right? For example, we can compare group 1 and group 2 combined, right? So we can combine group 1 and group 2 into one chunk, and then compare to group 3. That would be our second chunk of variability. So and compare these two, right? It doesn't have to be, it's not that one chunk is one group. That's why I call them chunks and not groups. And so the other, so another important rule is that if a group has been singled out in a contrast, right? So if we have compared, for example, right, as I just said, if we put group 1 and 2 in one chunk and compared to group 3, then this group 3 who was singled out and is basically was its own chunk shouldn't be used in another contrast. So otherwise it would be dependent, right? So that would be non-independent. As I said before, sometimes you have to do it, and it's not inherently wrong. It just makes things a little bit more complicated, right? Because the comparisons are no longer independent, so they're correlated. All right. So, and typically we have, or if you define orthogonal contrast, you should end up with one less contrast than number of groups. Right. So if you have 3 groups, then you have 2 contrasts, 2 orthogonal contrasts. If you have 4 groups, you have 3 orthogonal contrasts, right? So they don't have to be identical, so there are different ways of defining them, but you cannot have more than 2 orthogonal contrasts for 3 groups. So, and if we, so just to, this is just to demonstrate that issue to you, right? If we had 3 groups and we would compare group 1 and group 2 and group 3, and then group 1 and group 3, then one of these contrasts would be meaningless. And why is that the case? So that is because it's just, right? So it contains only redundant information. So it's completely dependent on the other 2 contrasts, right? So we can just add, so if we just add the first contrast and the second contrast, then these 2 contrasts are the third contrast, right? So they're basically just a transformation, so that the third contrast is just a transformation of the first 2. That's why it's yeah, not meaningful, not sensible to do that. Okay, so let's take a more concrete example, so to make it clearer, so how we define those contrasts and what is meant by like breaking down the model variability into these chunks. And so there's an example from a different textbook. So that always uses some unconventional data sets. And so here, so the idea was to test the libido of 3 groups of participants, so that were taking either placebo or a low dose Viagra medication or high dose Viagra medication. And then they were, so that basically, right? So these were the 3 groups. So one factor, right? That was a Viagra dose. And then, so the dependent variable was the participant's libido. Okay, So, and let's think about that, right? So intuitively, what might we expect to happen in such an experimental setup, right? So we have the placebos, a low dose and the high dose group. And these are just some cartoon data here, right? So, I mean, would be reasonable to assume that people who have taken so the Viagra drug, so either low dose or high dose, have overall, so that people, so basically participants in these two groups, have a higher libido than the placebo group, right? So that might be one reasonable hypothesis. And then another reasonable hypothesis might be that the high dose group has a higher libido than the low dose group, right? So, and that is how many experiments are set up, right? So you have some sort of control or baseline condition, and then you have so often multiple experimental conditions. And then a very sensible first contrast is to compare your experimental conditions to the, so as a whole, right, to the baseline condition, and then in subsequent contrast, you're comparing the experimental groups to each other. Okay. That's what I just explained. All right, so that is just a visual illustration of that principle, right? So here, so this rectangle here represents the so the model sum of squares, so the variance and the dependent variables, so the variance and libido that is explained by so by our model. So it means that is explained by belonging to either the placebo group or the low dose or the high dose group, right? So, and then we further break down so this model variability into so basically the variance that is explained by belonging to one of the two experimental groups versus so the placebo group. So that's our first contrast. And then so the second contrast would be to take, right, and then the placebo group is done. And so, and then our second orthogonal contrast would be to further break down so this chunk of variability here and to compare the low dose with the high dose groups. Right, and so we can also do something if we have similar, if we have more than 3 conditions. So let's say we have one control group and 3 experimental groups, right? So the first contrast would, again, so you can do it in other ways as well, right? So that's just an example. So first contrast might be to have the control group versus the 3 experimental groups. Then you break down the experimental groups, so into like experimental group 1 and 2 versus 3, and then you compare the remaining 2 experimental conditions here, right? And I have 3 contrasts. Another way, so to break down the variability in the 4-group design might be, so if you have 2 control groups, right? So then you compare the 2 experimental groups versus 2 control groups, and then you may be interested in comparing the experimental groups as well. That might be something that you're actually not interested in, right? So you could, so they're still orthogonal, right? So here, because they're, so you're not reusing, so the same chunk in multiple comparisons. But so still, as taking into account, keeping in mind what I told you earlier, that so you actually may want to adjust your so your p levels with the number of comparisons, even if it's a planned comparison. You may actually not want to do something that you don't have to, right? So I mean, control groups are control groups, and if you're not interested in the difference between the control groups for theoretical reasons, so then this might not be necessary at all here, this comparison. So here, these are a number of rules, and those are just like some guidelines when you're doing your initial attempts to define contrast. So once you have understood how this works, so it's very easy, it's not hard. So and then the rules are actually much more complicated than assigning the contrast weights. So, but I think in order to get started, they're helpful. So, and so there are 5 rules that you can use to define those contrasts and to either enter them into R or what other software you want to use, right? The first rule is that so groups that are coded with positive weights are compared to the groups coded with negative weights, right? So here, if you go back to this original example, our contrast 1 here, if we want to compare these two chunks, right, E1 and E2 versus C2 and C1, so then we would code these with positive weights and these with negative weights. Or the other way around, right? We could also code those with positive weights and these here with negative weights. Doesn't matter. So which is which? It's basically experimental minus control or control minus experimental. Doesn't matter. Difference is the same, right? Just the sign changes. But that's meant by the first rule, right? So so basically all the groups in one chunk have the same sign, and they have opposite signs, right? So they're different chunks of opposite signs. All right, that is rule one, right? So positive weights to groups coded with, compared to groups coded with negative weights. Then the rule two is, so the sum of the weights for comparison should be 0, right? So that means if I assign weights, right, to, and if I sum up the weights, say assigned to all 4 groups, then those should equal to 0, right? So for this first comparison, I could, for example, assign 1 into 1 to the 2 experimental groups and a -1 and -1 to the 2 control groups, right? If I would add them together, I would have 0. So that is the second rule. The third rule is if a group is not involved in a comparison, we assign it a weight of 0. Yeah, so again, going back to our previous example. So if we are comparing E1 and E2, then we might give E1 the weight 1, E2 the weight -1, and basically C1 and C2 would both code it with a 0. Right. So, and then for a given contrast, so the weights that we assign to the groups in one chunk of variation should be equal to the number of groups in the opposite chunk of variation. So that is can be a little bit confusing rule because it's not necessary to do that. So you can contrast, you can code the contrast in a different way, but so if you do it, you're not making a mistake, right? And it's good, it's helpful if you wanted to do it in a little more mechanical way at the beginning when you're not 100% sure yet. And then the fifth rule is, so if a group is singled out in a comparison, then that group should not be reused in any subsequent contrast. So I mentioned that earlier already. So that means if we wanted to code our contrast for, right, so our first contrast for this placebo Viagra example, so then we wanted to compare the 2 experimental groups so that had either low dose or high dose Viagra to the placebo condition, right? So that means the first thing is rule 1, right? So groups that are, so we basically want to assign opposite signs to the groups that we want to compare, right? So placebo gets a minus sign, low dose and high dose get a positive sign. All right, so then the sum of the weights for comparison should be 0. All righty, so that's also true here, right? So maybe it's better actually to to start with rule 4. So that the weights assigned to the groups in one chunk of variation should be equal to the number of groups in the opposite chunk of variation. Okay, so let's see. So first, so for the first chunk here, that's our placebo, right? So how many groups do we have in the opposite chunk? 2. Okay, so then we assign placebo -2, right? And here for so for the experimental groups, Viagra groups, so how many groups do we have in the opposite chunk? 1, so we assign it 1, right? And we set positive weight, so 1, 1. Okay, we check, that sums up to 0, all good. I think we can move on to the next contrast. So that is our right placebo versus high dose and low dose combined. And then, so the next contrast combines low dose and high dose. That's relatively easy, right? So now we assign a -1 to low dose, a 1 to high dose. We could also do it the other way around, it really doesn't matter. It makes a little bit more sense because we would expect for the high dose a higher libido value, right? So it would make more sense to subtract the low dose from the high dose, but mathematically it really doesn't make a difference or for any of your significance, whatever. Unless you do a one-sided test, right? So that would be the only case where it makes a difference if you want to do a t-test. So if you specifically test the hypothesis, so let me just jumping over, maybe going too quickly over that. If you wanted to specifically test the hypothesis that your high dose group has a higher libido than the low dose group, you have to be careful, and you want to do a one-sided test, right? You want to do a t-test and a one-sided test. You have to be careful that you that you're basically assign the weights in the right order, so that you actually have the right difference, right? So that you put your, that you read your results the right way, right? That you look at the right tail of your t-distribution, right? Otherwise, not as a wrong tail. So then you have a problem, right? So does it make sense, right? If so, you expect high dose to be higher than low dose. So then you don't want to look at the left tail. You want to look at the right tail. Okay. So okay, what else did I want to say? Right, and then we see that in this so second contrast, the unused group, there's a group that is not part of the comparison, is just assigned to 0. Yeah. Okay, hope that makes sense. Right, so R is actually really helpful in defining or using those contrasts, because it has a bunch of predefined contrast functions. So as I said, so that you can use, especially when you do it first time. So you might want to rely on what's already defined in R, but it's really not that hard to do it yourself. You will get used to it very quickly. So it's not a big deal. So, and what we are doing is we just have to set a contrast attribute to our grouping variable. So that means the our variable that defines a factor in our ANOVA, right? So our yeah. So in the placebo and the Viagra example, that would be so a factor that's called like Viagra group or dose condition, something like that, right? So and then you use a function that's called contrast. Assign so this factor, your factor, a certain attribute, so the contrast attribute, and tell R what it is, and either so you assign it a contrast that you have defined yourself, and it is really just a simple vector, right? It's just a numeric vector with these numbers that we just looked at, right? It could be like 2, -1, -1. 0, -1, 1, right? So these are really just numeric vectors, and you assign them, so using the contrast function, to your factor in your data frame, and set it as a contrast attribute, right? So then your factor has an additional attribute, an additional property, you can call it. And then after adding this contrast attribute to your factor, to the variable in your data frame, you run your ANOVA model, so you fit the model as usual using LM or AOV. Yeah. And then you get your output that reflects the coefficients for the corresponding for the corresponding contrast, right? So the way you coded them. And as a matter of fact, R is doing that per default anyway, right? So it's some sort of coding, we have learned about that. Last time, some sort of coding is always involved. And so per default, if you don't tell R anything else, it will do a dummy coding. So where it assigns as basically a 1. If, for example, in our Viagra examples, a dummy coding would be just 1 and then 0, 0, right? So for the plus, so if you would input the data in the same order, right? If placebo would be our first condition, then the dummy coding would assign placebo a 0. Sorry, and then low dose for the first contrast of 1, and the high dose is 0, and then the next contrast would be 0 for placebo again, because it's right. Remember, so the first your first level is a reference category, so R treats the first level of your factor as a reference category, so that is assigned all 0s. And then so for the second contrast, so the coding would be 0 for placebo, 0 for a low dose, and 1 for high dose. So that is what R does if you don't tell it to do anything else. As I said, so there are a number of predefined contrast functions in R. And one that is used frequently is the so-called Helmut contrast. And so the coefficients so that you get from fitting a model with a Helmholtz contrast, compare each level of your factor with the average of the preceding ones. Right? Sounds a little bit odd. So that means, so you contrast the second level with the first one, right? In our example, you would contrast the placebo, so the low dose with the placebo. And then the third level was the average of the first two. So that means in our Viagra example, it would be the high dose versus low dose and placebo combined. And then if you had a fourth level, right, you would contrast the fourth level with the average of the first three, etc., right? And in that contrast coding scheme, so the intercept would reflect the grand mean, right? Remember, there was a dummy coding. So the intercept reflected the mean of the reference category, right? So here would be the placebo group. For Helmholtz contrast, the intercept is a grand mean, right? So it's the average of all three group means, or depending on how many groups you have, right? Okay, so and Helmholtz contrasts are orthogonal contrasts, so they're independent. Then you can define the polynomial contrast. So they're also called trend tests. So that and those are a series of orthogonal polynomials, right? So it starts with a linear comparison, and then the next one is a quadratic, a cubic, a quartic, etc., trend. So, and they're entered sequentially. So that means the first thing that is tested is a linear trend. And then so you test the residuals. So our test the residuals for a quadratic trend and then a cubic trend, etc. So the third very common option is the so sum to zero contrast. So it's also called effect coding or deviation contrast. And here so the coefficients that result from a model that is fitted using so effect coding compare each level with a grand mean. So that means the regression weights, right, that you're getting, your betas reflects a difference between each level and the grand mean. And the way it's coded is very similar to the dummy coding. The only difference is that so the reference, so-called ref, is not really a reference category anymore, right? Because the coefficients reflect actually difference to the grand mean, not to a particular reference, not to a particular category, but there's still some implicit reference. So there is one group that is assigned -1 across all contrasts. Yeah, so in dummy coding, we had this baseline condition that always has a 0. And in effect coding, you have a condition that is always assigned a -1. So basically, you're in your individual contrast, you're always contrasting a particular group or a particular condition to this condition, right? But the beta coefficients reflect the difference of a certain group mean to the grand mean. And then, so the treatment contrast is nothing but the dummy coding that we have already talked about, and that is the default, right? So if you do not do anything else, and this is not orthogonal, right? So those contrasts are not orthogonal, so because we're reusing, right? So so you might have 1 versus 2 and 1 versus 3, for example. So they're not orthogonal, they're not independent. All right, so let's just do some example. Just let me check whether I wanted to do anything else. Oh yeah, right. So that's an important. I will also mention that in the tutorial. R also differentiates between ordered and non-ordered factors. So and for any factors that are ordered, and you have to, when you specify as a factor, you have explicitly tell R so you have to set the so the option ordered, or the argument ordered, to true. So for ordered factors, so as a default, that R uses as a contrast as a polynomial contrast, and for unordered, for non-ordered factors, which is R assuming if you don't tell it anything else. So it uses a treatment contrast, right? So dummy coding, which we had already talked about. Right. Okay, so this is just to give you an example how it would look like in R. So there are will be more examples in the Markdown. There's also an example in the tutorials. So if you wanted to do a Helmut contrast for our Viagra example, then right, so let's assume we have a data set, right, a data frame that's called Viagra.data, and it has a variable that's called dose. And so this would have the values placebo, high and low, right? So that would be our factor here. So then we use a contrast function, right? And to set the the attribute of the factor dose to Helmut. So the right, so that R knows that you want to use a Helmut contrast for this factor. And then so you just have to specify the number of levels, which in this case are 3. Right, so you have 3 groups, 3 levels. And then so you fit your model the same way that you would do anyway, right? So make sure that you always, right, you have to specify the contrast before fitting the model. And then you can look at the summary of your model fitting, and you get the usual output, right? So you get your estimate for the intercept, which for the, right, remember, so it's 3.466. And for the Helmut contrast, just mentioned that this is the grand mean, so it's the mean of all group means. So that's a corresponding standard error here, right? And then the t-value, just the estimate divided by the standard error and your corresponding p-statistic, which in this case just tells you the group mean is significantly different from 0 and not very interesting, right? So, okay, and that is a mean of the placebo group, yeah, right? Sorry, it is a grand mean. We're not in dummy coding. So that is a grand mean. So it's a mean of all group means. So placebo, low, and high dose. All right, and then your first contrast was so right, the first level, which in this case is placebo, versus the second level. Right, so this so the mean of the first 2, and then what your so that is your first contrast, right? It contrasts the so the placebo condition versus the so the low dose condition. Sorry, my computer went mad here. So, and the coefficient of 0.5 actually reflects the mean of the first 2 level minus the first level. Right? It's a little bit more, yeah, not as straightforward as the other contrast definitions. Okay, so then everything else is the same, right? So our standard error, so that's a t-value. In this case here, it's not significant. So that means that's a difference between so the first and so the placebo and the low dose is, yeah, not significantly different from 0. And then our second comparison is the so is the third level. So in this case, our high dose versus the first 2, right? So the average of the first 2. So the high dose versus average of placebo and low dose. So that is a mean of all 3 levels minus the mean of the first 2 levels. And that is, again, significant, right? So that means that the high dose group differs significantly from the other 2 conditions combined. All right, and right, so these are our regression coefficients, right? Our betas here, as usual, standard errors, and then corresponding t-values, that's the corresponding p-values. Okay, and if you, after defining the contrast, right, if you type into R Viagra.data.dose, you also see, so that the column now has an attribute, it's called contrast. And then it tells you what the elements are. So there are 2 contrasts defined. So the first one, right, so is the one that compares so the placebo versus the low dose, right? Placebo versus low dose. And the second one compares placebo and low dose versus high dose. Okay. So this is just an additional hint. It's not theoretically important, but you noticed, right? So if you're fitting our LM, so our model using LM, so it will just tell us dose 1, dose 2 here. but we don't really, that's a bit misleading because we don't actually know what the contrast coding is like. So if you want more meaningful labels, so you have to do it a little bit differently. So you have to add the column names. So you can do that, right? So here you saw that it's empty, right? So there are no names. You can actually give your contrast names. So these would be the column names, right? Not all, so the row names are your 1 and 2, right? So in order to do so, you can basically just use a call names function. And then, so here you define what's the name of the different contrast should be, right? So I call them placebo versus low, and placebo versus and low versus high. I mean, it's maybe not the most straightforward thing, but you can do it whatever makes sense to you, right? And then, so R will insert that after, so the name of the factor, right? Right, so then you have placebo versus low and placebo versus high. Placebo and low versus high, which, so we'll tell you what's actually in there. Okay, so you can, of course, also get the traditional ANOVA output that shows your F values and your sum of squares. So you just have to use AOV, right, to fit your model. And then you use the summary function. And then again, if you want, so if you use AOV, then so you have to use this split argument here in order to get so the output organized in a nicer way. Otherwise, R will give you some cryptic information, right? So it will just, I'm not sure what it's doing for AOV, whether it also gives you a dose 1 and dose 2 or something else. But so you have to type a little bit more here, right? So what is 1 and what is 2, if you want that, if you want to be remembered what the what the contrast actually mean. Yeah. And so you also see that so here you get your degrees of freedom for your contrast, right? So for your additional or your predictors here. So in addition to the overall model, right? So the overall effect of dose. And you can see that the degrees of freedom are 1, and they're always 1 for contrast because we're comparing 2 chunks of variation, right? Two. So we're basically comparing something like 2 means, right? Of course, there are more groups involved in many cases, but we are comparing 2 chunks of variance. So it means 2 minus 1, yeah, is 1 degree of freedom for each contrast, always the same. All right, and then you get your traditional output. Okay. Yeah, and then so what you're using, whether you're using AOV or LM, it's your personal preference. So they're equivalent. So you can use one or the other, whatever you like better. Okay, so if you let's now move on to the case where you want to define a custom contrast, right? So you want to define your own contrast. So nothing that R has predefined for you already. So then you could basically, as I said, it's nothing but a vector, right? And you just give it a name. So here I gave it this like sort of cryptic name, but you can give it any other. You can call it contrast 1 or my preferred contrast, or right? So just a name here, just a name for this vector. So and just be sure that so the way you're defining, so the order of your of the numbers in your vector correspond to the order of your levels. Yeah. So here in this example, it's placebo, low, high. So make sure that it corresponds to how the so your levels are ordered, right? So otherwise you get nonsensical output, or you're comparing conditions that you actually do not want to compare. And so for the experimental versus control, right? So I say placebo versus so low and high, and then low versus high is just placebo is not part of it, and then just low versus high. And so then you basically assign the contrast to your dose factor, same way as we did before, right? So you just have to use the column bind function. All right. So to basically bind them together, so 2 vectors. just a format that R expects. So no magic to that. All right. So and then right, if you check what happens after assigning this so your individual contrast vectors. So you see that now. So you have your right. So your name is the names of your vectors. Another nice side effect, right? So you have, if you define the contrast yourself, you always have some nice names that are meaningful to you, and don't have to go that take that extra step to name them later on. And so, right, it's always good to check that you actually have the coding that you want to have, right? So it's always good to double check after you have assigned your contrast codings, that so it really corresponds to the correct levels here. All right. Okay. So let's talk about polynomial contrast, which is also known as trend analysis. So let's assume, orthogonal, I mean polynomial contrast. So I will calculate almost everything you ask it to do. So, but a polynomial contrast or trend analysis are only meaningful if your levels, so the dependent variable or your levels, that depends. If the differences between the levels of your factor in the dependent variable are equidistant, right? So that means if you have like levels 1 to 10, so let's assume we would have an experiment where so we have like 5 different Viagra doses, then the placebo we could assign placebo 0, and then we have levels 1, 2, 3, 4, 5. So and assign these numbers. Then we have to make sure that actually the dose 2 is really twice as much as dose 1, right? So dose 1 is 1 milligram, and dose 2 is 2 milligrams, and dose 3 is 3 milligrams. I'm just making that up. And not that dose 1 is 1 milligram and dose 2 is 5, and then dose 3 is, I don't know, 20, right? So that wouldn't make sense. So we have to make sure that, so they're basically correspond to interval scale levels then. Okay. So, and if you wish to test for a significant trend, yeah, in the sequential sense, yeah, if for example in this, let's assume, so we're again talking about our Viagra case here. So if we expect that something like that will be the case, so that our libido will increase across the levels in a linear way, yeah, so if that is 1 milligram, these are 2 milligrams, these are 3, 4, 5. Right, so that would be a linear trend, and we can test that trend across the levels of our factor. Right, we can also we could also assume, well, it's a quadratic trend, right? So we assume that up to like a certain dose, so we have an increase, but then actually has the opposite effect, so then decreases libido. Or right, there are obviously some more complicated patterns like a cubic trend or quadratic trend. I mean, but that is rather unlikely unless you have good reason to assume that. So usually anything but beyond a cubic trend, I have never seen anything like that. There might be, I mean, what do I know, right? So there might be cases where it makes sense. All right. So and then the way so the polynomial contrast work is, of course, you can always set up your own basically contrast. And for example, if you only want to test for quadratic trend, you can set up your model in that way. Does it make sense? You have to decide that. But if you specify the polynomial contrast so in R, so then it will basically, R will first fit the linear trend. Then it will take the residuals. So basically, after eliminating the linear trend, it will test the residuals for quadratic trend. Then it will take out the quadratic trend, will test for cubic trend, etc. Right? So it's basically, right, is there any higher order trend above and beyond the lower order trend? So that's how it works in R. All right. So and right, so if we would do that for our Viagra example, so then we would set it to contrast poly, again 3 levels. And then, right, so we are again creating our model and access our model summary. And so, and then it gives us here the coefficients, right? So for the linear trend and the quadratic trend. So, so why does it only linear and quadratic? Good question, right? So remember we had only so 3 levels, right? So, and then, so you need to take into account that in order to define a linear trend, you need at least 2 data points, right? So you cannot define a linear trend if you have not at least 2 levels, so 2 data points. It means fitting a linear trend requires 2 levels, 2 groups at minimum. If you want to model a quadratic trend, you need at least 3 data points, right? Otherwise you cannot model, so otherwise it will always be linear, right? So in order to model a quadratic trend, you need at least 3 data points. For cubic data, for a cubic trend, you need at least 4, right? Because it has to rise, fall, rise again. So that requires at least 4 data points, right, to see that pattern. And that is a reason we have only 3 levels in our example, right? So we have only placebo, low dose, high dose. So that means we cannot model more than a quadratic trend, right? So that's all we can do. And then if we had 4 levels, we could do a cube, then I would output a cubic. If we had 5 levels, it would output a quadratic, etc., etc., etc. Okay, so that much about contrast. And again, so these contrasts are typically used for really, really strong a priori defined hypotheses. And so you may want to combine them with some correction for multiple comparison as well, right? So for example, Bonferroni, which is for a low number of comparisons, a powerful procedure. Right? We'll talk about them right now. So the different options. So post hoc tests in the traditional sense are really tests that so you have no a priori hypothesis regarding specific group differences, right? So that's when you do post hoc tests. And so often you want to compare so each mean against all others. Yeah, you don't have to, right? Keep that in mind. So you don't have to. Don't compare more than you have to, because you lose power by just wasting, right? So being wasteful and comparing everything with everything, losing power. No, don't do it if you don't have to. Okay, yeah, we mentioned that already. So and we call those methods also multiple comparison methods. So they fix a problem so that you have an inflation of the type 1 error rate if you conduct multiple tests on the same sample. And so, so they basically make sure that you have this family-wise error rate. That means so by performing n number of tests simultaneously. So, right, so you still maintain your 5% error rate or error probability, right? So rather than having some insane number. All right, yeah, so that so the probability that at least one significant difference equals 0.05, not more, right? So 5%, that at least that we are making one mistake now. So we don't want to make at least one error at 10%, 20%, 30%. Yeah, and I just included that here one more time because it's less common actually to ask for that in regression analysis. I don't know why, because especially if the model is complex, you should do it. I mean, if you do it for for other comparisons, so you should also do it for regression coefficients in a model. So just keep that in mind, right? So that if you have a very complex model and if you have predictors that are not backed up by a lot of research, then you probably want to use a multiple comparison correction methods as well. Okay, so our simplest example and also the most popular one is the Bonferroni adjustment method. So and it's very, yeah, it's very straightforward. So you just divide your alpha level by the number of tests that you're performing. So let's say you want to do 4 comparisons, right? So then you divide your 0.05 by 4. Yeah, and that means that basically, so when you're now doing your individual comparisons, then nothing is significant that is larger than 0.0125, right? But keep in mind that your alpha level is still 0.05, just your family-wise, right? No, that you want to make sure that your family-wise error rate does not exceed the 5%. Okay, the Bonferroni adjustment is conservative. So it's a conservative one, right? So it's especially if you have a high number of individual comparisons, right? It's doing okay. It's not doing okay job. Its power is actually not bad for a low number of post-hoc comparisons. So that's what makes it a good method if you want to, for example, correct for multiple comparisons for regression coefficients. If you have less than 10 predictors in your model, yeah, if you have something like 4 predictors or so, and so also if you want to control your family-wise error rate for a limited number of planned contrasts, right? If you want to be on the safe side. All right. So the reason that, so let me just go back. So you may wonder, so why we are, actually I was wondering about that. So it took me a while to, I remember then when I was a student, so it always surprised me that you're actually dividing by the number of tests, because 2 weeks ago, remember, so we were doing this calculation that you actually have, it's actually to basically the alpha error inflation or type 1 error inflation is to the power of alpha, right? Because if you're conducting 2, so the probability of not making a mistake is 0.95 times 0.95, right? And 2 tests, and then 0.95 times 0.95 times 0.95 and 3 tests. I thought, well, why are we not taking no, or am I not reversing the power function? What is it called? It's a square. It's not a square. It's a root, but not a square root. But so right. But actually, because alpha is so small, it's just to make it a little bit easier. Because alpha is so small, so actually, so that if you take the 1 minus alpha to the power, or power of 3 or so, it's almost the same as taking 3 times 1 minus alpha. So that's why you can actually divide by the number of tests rather than reversing the power function, right? Okay, just in case you wonder about that. All right, so these here are more popular options. So in addition to Bonferroni, so which is also often called Dunn's method or Dunn's test, right? So when you ever see that Dunn's test, it's based on the same idea as the Bonferroni adjustment. So one other popular option is the so-called Chaffee test, or the adjustment method. And so this is the most conservative one, right? It's even more conservative than Bonferroni. And it's only if you really, so basically it's designed to protect against type 1 error inflation when all possible simple comparisons are made. Yeah. So that means if you compare all factor level combinations, so basically all your cells in your design with each other, right? So in not only individually, but also grouped together, etc., etc. So that means it's more than, so if you have k number of groups, so it's more than k minus 1 comparisons. So it makes sure that no matter how many, so even if you run all possible comparisons that you could make and right, you can dream of, right? So it will make sure that your family-wise error rate does not exceed your predefined alpha level. And therefore it's very, very, very conservative. So use it only if you're really interested in if you want to like explore all options, right? If it's like an absolutely exploratory study and you really want to look into each individual comparison that you can think of, right? So then this is an appropriate procedure. In almost all other cases, it will be too conservative. Yeah, Bonferroni is also conservative, but less conservative, especially so with a fewer number of comparisons. Okay. So, and you should use these methods in particular, so either Jaffe or Bonferroni, if you have a large number of comparisons that you want to make, right? If it's more than k minus 1. So if you the number of levels minus 1. All right. So then another popular method is a Newman I don't know it. Newman. How would you pronounce it? Coults, Newman Coults.
I would
So
say close.
okay. Yeah, thank you. And it's a step-down procedure. So it's a stepped approach. So that means you're basically always comparing. So first you order the means of all groups. So in ascending or descending order, doesn't matter. And then you take the largest and the smallest means and you test them for significant differences. And if those means are different, then you next test the smallest with the largest, blah, 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 until you reach a comparison that is not significant. That's why it's called a step procedure. And it's less than it's less conservative than Bonferroni, so that means you have more power, but it's also not free of controversy. So it's so some people don't like it. So it's usually not the first choice if you read what's recommended. So most people really like Tukey's HST, so the honestly significant differences. So that is something that you see very frequently in publications, and it's also often recommended as a middle ground, right, between power but still tight type 1 error rate control, and it provides definitely more protection than so the first option, but it is only more powerful than Bonferroni if you have a relatively large number of groups or single comparisons that you want to make. So a rule of thumb is if you want to make 6 or more comparisons, then so it's a better choice than Bonferroni. If you want to make less than 6, then Bonferroni is a better option, right? If you have, as I said, if you have a relatively low number of comparisons, always go with Bonferroni. Well, it's easy and gives you usually a good gives you like good compromise between power and control. And so another popular option is Holm. So Holm is also a stepped approach. So it's not basically the stepping mechanism is not based on the group means, but it's based on the p-values for the comparisons. So basically you define beforehand which groups you want to compare. Then you calculate, I mean not you, but R will do it for you or your software. Then so the software calculates, computes the p-values for these comparisons. And then you order these p-values from small to large, right? So, and then your critical p-value, so the one that you adopt for the post hoc comparisons for a given contrast, is just so your nominal alpha level, so the one that you, for example, 5%, and so then you divide it by the number of comparisons, right? So that means for the first comparison you're making, the Holm adjustment is identical to Bonferroni. Yeah? If you want to do 6 comparisons, right? So then you divide alpha by 6, and that is basically the threshold for your smallest p-value. If the p-value is larger than alpha over 6, then nothing is significant, right? You can immediately stop. If it's smaller, then I say, fine, this contrast or this comparison is significant. Now I move on to the next one, so to the second smallest p-value. And now you divide it by 5, because you have only 5 tests left, right? And then if it passes, you move on and you say, okay, now I take the third smallest and I divide it by 4, because that's what I have left. And say if it's still right, so lower than the threshold, and you keep going and you stop when so once the so your empirical p-value is larger, right? Then the defined one or the adjusted one, and then you know that all other remaining contrasts also comparisons are also non-significant. So that is the idea, right? And then so another option so that I'm just including because it's part of many statistical software packages, but it's usually not recommended, is Fisher's LSD. So, and Fisher's LSD is actually doing nothing. So it does not correct at all. And the underlying rationale is that you do post-hoc comparisons only if you have a significant overall ANOVA. So this is basically your protection mechanism. But it has been shown multiple times that you still have type 1 error inflation. So that is not enough. So you should not use Fisher's LSD, and especially not if you have more than 3 groups or 3 comparisons that you want to make, right? So, but better do not use it. Yeah, I'm just including it for sake of completeness here. So if you have, if you want to compare less than, so k-1 groups, not only that you do, again, so also for your post-hoc comparisons, you don't necessarily need to compare individual groups, right? So you can also compare group 2 and 3 versus group 4 and 5, right? So you don't have to take, right? So you don't have to do that for individual groups. You can also cluster them. So, but if you have like a relatively low number of comparisons, so that means less than k-1, then so you can also consider Hochberg's and Hummel's methods, and they're also stepped approaches, and so they give strong control of the family-wise error rate, but are less conservative than Bonferroni. However, keep in mind that they're only valid when the hypothesis tests are independent. Yeah, so don't use them if you want to test all possible comparisons, or if you have these overlapping comparisons, right? If you want to test group 1 versus group 3 and group 1 versus group 2 and group 3 versus group 4, doesn't work. Yeah, so that you cannot do that with Hochberg and Hummel. Yeah, so use a different one. Then, all right. So in addition to to controlling the family-wise error rate, so it has also been suggested to actually so instead of obsessing with the type 1 error rate, you could also choose a different approach that is slightly less conservative, and basically what you want to make so in that mindset. So what should be controlled is how many of your rejected null hypotheses, so how many of the null hypotheses that you reject when doing your comparisons are actually falsely rejected, right? So what is your within these, within those, let's say you're rejecting 10 null hypotheses, right? So how many, so basically you try to estimate how many of those are falsely rejected. So how many of those are true. And so this is a different approach, and it's called the false discovery rate, right? So that is different from the family-wise error rate. So from the making sure that the type 1 error rate is controlled versus simultaneous testing. So procedures that use the false discovery rate adjustment. So permanent examples are the Benjamini and Hochberg procedure, or the Benjamini and Yekutieli procedure. So they're very similar. So the difference is then that so the BH is for independent comparisons only, the same that I told you about Hummel and Hochberg earlier, whereas the BY criterion can also be used for dependent comparisons, right? So if you basically test overlapping groups here, or groups are overlapping between your across your contrast, so then you should use a BY, and they're less stringent than, so the false discovery rate is generally less stringent than the family-wise error rate correction control method. All right. Yeah, so this is just an explanation. It's actually not super important. I'm just including that for you to give you like a little bit of background. So that's a so it's very basically the Benjamini Hochberg is similar to the Holm procedure, and that is also stepwise. I mean, many are stepwise, right? So to improve or to make the idea of the Bonferroni adjustment less conservative. Of course, the BH criterion also uses false discovery rate, not family-wise error rate. So it's a quite different concept. But it's also a step procedure in the sense that it starts by computing all p-values for all pairwise comparisons, or all the comparisons that you want to make. But it ordered them from large to small. So actually starts with the largest p-value. And then, for the first comparison, it's again identical to the Bonferroni correction. You just divide your alpha, your nominal alpha level, by the number of comparisons that you're making. And then, if you basically move on to the to other comparisons, you use a more liberal criterion, right? So you basically just divide by the number of the remaining values, right? So this is basically just the comparisons that you have left, and so it is basically the other way around. So once you basically, as soon as you meet the threshold, so basically probably your first contrast will be non-significant, and as soon as you hit the significant threshold, then you can stop testing, and all the rest of the comparisons will be significant, right? Okay. So how you conduct post-hoc tests in R depends a little bit on which test you would like to do, because at least to my knowledge, maybe there are updates because there's constantly development with R, right? So constantly like new packages are added, new functions. So I cannot guarantee that my information is always most up to date. But to my knowledge, there is not a single library or not a single package that has all procedures available. So many of the most common ones are part of the base system. And so they are implemented as a function pairwise t-test, right? That's Bonferroni, Holm, Hochberg, Hummel, BH, and CBY criteria, for example. That's not all, so there are more. Then, so there's a library post-hoc tests. That's a function post-hoc tests in the desk tools library that has also a bunch of really prominent correction methods. And then finally, there's the GLHT function. So in the multcomp package, and that has the added benefit that so you can use it for contrast or post-hoc comparisons if you have an unbalanced design. So I haven't mentioned that earlier, but so basically all of these procedures here, and also the way they're implemented in these libraries, implicitly assume that your design is balanced, so that you have the same number of subjects in each group. If that's not the case, so then they're a bit biased. So, and so in that case, it might be better to use a GLHT function from the multcomp library, so because it can deal with the unbalanced designs, it allows the predictors to be correlated. Yeah, but what happens? So that happens when you have an unbalanced design, right? So it uses a multivariate t-distribution rather than the bivariate, but it's not as a univariate. So, but these are just details that are not really important for practical reasons. I just want you to remember, if you have an unbalanced design, I would recommend to use a GLHT function, so you're on the safe side doing that. All right, yeah. So one last word that I wanted to mention, right? If you have any doubt about the underlying assumptions, so for example, if you're not sure whether you have the homogeneous variances across your groups, etc., you have to use robust post-hoc tests as well, right? So, so it's not enough to do only a robust overall ANOVA. So you have to apply the same criteria to your post-hoc test. Yeah. And also the fewer comparisons you're making, so the more similar the difference are. So the less it matters which specific method you're using. Okay, so here, these are just a few examples for the most prominent procedures. And so here's a Bonferroni correction method is implemented in the pairwise t-test function, right? So it comes with the base system. And then, so basically just calls a function, and then so you pass your two variables of interest as arguments, right? So that is your dependent variable here, that is your factor, right? So it's libido, that's the outcome, so it's your factor, right? It's a dose. And then you have to define what adjustment method you want to use, in this case, Bonferroni. And then this is your result, right, for all your comparisons. And you can see that so 0.25 for is only basically the comparison between level 1 or group 1 and 3, that is between placebo and high dose is significant here. Okay, and if you want to do home, right, so you can also use the same function, everything's identical, just use a different adjustment method. And you can see here, as we had just discussed, so the p-value for the first comparison with the smallest p-value is identical to Bonferroni. But then if you compare, right, so the other two numbers, then you can see that home is actually much more liberal. So it had, or you could say it has more power than Bonferroni. See how much stricter Bonferroni is for the other comparisons, especially the third one. So that shows you how with the increasing number of comparisons, it's really getting harder to get significant result. Okay, so that's the so the criterion that controls a false discovery rate for dependent comparisons. Now it's the BY criterion, so it's also implemented in the same function. And so you see that's actually even, it is more conservative, right, for the than Bonferroni for the first comparison, so for the largest difference. But then it's more powerful for the other ones, right, because it also relies on the stepped approach, so that it's more getting more liberal with the increasing number of comparisons than compared to Bonferroni. And so if you want to use the honest significant differences, so have been such as by Tukey, so you can use a post hoc test function from the desk tools package. And so it also provides you with a confidence level in addition to like calculating the differences, right? So it has like a nice additional features. And so you can see it's less conservative than Bonferroni, but usually not as powerful as Holmes, right? It's somehow in between. Now you see that if you compare the, so again, the other, so the p-values for the other two comparisons, so you can see that it's, in this case, actually, it's not true. In this case, it's doing just as well as Holmes, but it's typically, right, not as powerful as Holmes. It might depend on the number of comparisons that are included in your analysis. Okay, so we could, of course, also, if we basically, in most cases, our software is giving us the confidence intervals, but so it's often also nice not only to have the, right, as always, not only have the p-values and the differences themselves, but also like a plausible size of the differences among the population means. That means we want to calculate the confidence intervals for our pairwise comparison of means. And so we do that very much in the equivalent way as we have done that for our right, group means or other parameter estimates. So yeah, we are just taking the empirical difference between our group means, and then we are subtracting and adding, so t times the our standard error. And that is weighted by the weighted group mean here, right? So sorry, group sizes. So this is the sample size for our first group, and that's the sample size for our second group here. All right, and that is a textbook example here where they just so study was conducted to compare the population mean ideology of Democrats, Independents, and Republicans, so these three groups. And then so they wanted to compare, so they wanted to determine the confidence interval for the difference between group 1 and group 2, group 1 and group 3, and group 2 and group 3, right? And confidence level is supposed to be 95%. And so if we want a family-wise error rate of 5% for our 3 comparisons, and we use Bonferroni, then you have to divide 0.5 by 3, right? So it leaves us with 0.0167 for each interval. And then you determine t-score for the corresponding degrees of freedom, right? So for either 2-tail probability or 1-tail probability. And so you have to, of course, also get your residual mean from your overall analysis. So the critical t-value here is 2.41 for the single-tail probability. And so then you can just plug in those numbers and calculate your confidence interval, right? And then you will get something like that here. That is basically for all these comparisons, right? So the Democrats versus independents, Republicans versus Democrats, and Republicans versus independents. So this is the observed difference between the groups. And then you can see that this is a Bonferroni corrected confidence interval, so the Tukey corrected confidence interval. And so the first comparison includes 0. So for the first comparison, so the confidence interval includes 0. So that would be non-significant, would correspond to non-significant difference, right? And then the other 2, so the confidence interval does not include 0. Okay. So, and you can also see this general trend that Tukey tends to be a little bit less conservative. So that means it's a little narrower here. So, nah, actually not really. It's the same here. I mean, it's also a really low number of comparisons. I mean, it's right. So it's not really narrower because it's lower here, but it's, no, it is, of course. It is, yeah, it's a little, so for this example, it's actually a little bit narrower, yes, as a Tukey, based on the Tukey honest significant differences. All right. Okay, and then as always, so we are interested in effect sizes. We have talked about effect sizes for the overall ANOVA, right? So about the omega squared. And so our eta squared, so omega squared just corrected for so this bias that eta squared has, right? So same as for R squared. And so we also want to determine so the effect size for our post hoc comparisons, right? So and for our contrast. So and right, we know that type 1 error rate and the power of a test are linked. So if a test is very conservative, we have a small type 1 error rate, but then it's also likely to lack a lot of power, right? So we have a type 2 error rate, a high type 2 error rate. So often we want to so find a good compromise, and so want to determine how many participants we need, right, to accomplish this compromise. But then we also have an idea of the effect size. That is realistic, and that's why it's always important to report effect sizes, right? Also in our publications. So in order to do that in R, so you can obtain many effect size measures for post hoc comparisons or pair-based comparisons using the MES function of the compute ES package, so compute effect size package, and it basically has almost everything. It has Cohen's d, right? So Cohen's d is just a standardized mean difference. It has Hedges g, that's an unbiased estimate of d, of Cohen's d. It has a correlation coefficient, has Fisher's z, and the log odds ratio. So it's basically all the most common ones, right? So for pair-based comparisons. And so it also computes your confidence intervals, variances, p-values, et cetera, et cetera. And the F-size package has common options too, right? So these are the 2 options for you if you want to compute that. And as you have seen before, so some other packages, if they do the so the pair-based comparisons, they actually also output the effect size measures, but not all of them. Right. Okay, if you want to do effect sizes for your contrast, for the orthogonal contrast, you can so use the omega squared the same way that you did for your overall, your omnibus ANOVA. So it basically you can interpret that in the very same way. It's just the percentage of variance in your dependent variable, right? So in this case, so the percentage of variance in libido that so you can account for by this particular contrast. It is accounted for by this particular contrast. For example, by the right comparison placebo condition versus experimental conditions, or the two high and low doses against each other. And so you can also calculate R as an effect size measure, which is just a correlation between the group means and the contrast values. A lot less common, but also not that unusual. So you see that quite a lot. All right, so we went over so the assumptions already, so that's why I would rather skip that for the moment. So it's also they're basically identical to all your regression assumptions. So they're just a little bit special. So as a reminder, in terms of the homoscedasticity assumption, so it's the same as for regression. The only difference is that now basically we don't have a continuous predictor, we have categorical predictors. So that's why so the homoscedasticity assumption equates to the variances in all groups are equal, right? So the variances in all cells. And if so this assumption is violated, you can use two corrected versions of the F ratio. So these are the Brown-Forsyth F or the Welch's F. So the Welch's F is always so the preferred method. It's more powerful. So what you do is you adjust the degrees of freedom when you're using these correction or these different tests. And in order to determine whether so the homogeneity of variance assumption is met, you will, so you have basically two options. You check the residual plot, which is always a good idea, right? In this case, you basically the residual plot shows you the residuals within each group. So for each condition, and then you can assess whether they look roughly similar or not. And you can do it using a formal test with Levene's test. We were talking about that, right? Which is equivalent to one-way ANOVA with the absolute value of the difference between the score and the mean of the course of the group it belongs to. Okay, and so here, right, that is just a syntax, how to do that in R. So it's a functional Levene test, and then you input again, so it's a dependent variable and the factor. So, right, and you can can also define what your as an additional argument what your center statistic is. So here's a median as a default, but you can change that to other values as well. And so for our examples, the test is not significant, which means we can maintain or keep the null hypothesis that the variances are equal between the three groups. So this is just an illustration that basically, if you had to correct so your degrees of freedom because Levene's test is significant, then what you want to do is Welch's test. And you can implement or you can run that using the one-way test function, right? So the syntax is almost identical otherwise to the LM command. So as you can see here, so that's your corrected F statistics. The numerator degrees of freedom are the same, right? So it's still 2. Right? We had 2 groups, so degrees of freedom is still 2. But your denominator degrees of freedom, so the residual degrees of freedom are adjusted, so they are lower, right? So in our original analysis was 57. Where is it? I can show it to you right now, but I have to believe me. Oh, here you see it, right? So in the original analysis was 57. And now it's considerably much lower, right? And that also basically makes the test more conservative because remember, so you have your residual mean squares in your denominator, right? So that means the smaller the residual mean squares, the better it is. So the larger your F statistic gets, and so the mean so the residual mean squares are calculated by dividing the residual sum of squares by the degrees of freedom. Ooh. If the degrees of freedom are smaller, residual sum of squares are larger, right? So which makes the F ratio smaller, right? And that makes the test more conservative. And I can also see that the p-value reflects that when you compare that to the analysis. Not this one is a different analysis, right? So it has just the same degrees of freedom, but if you compare that to the original F statistic. Okay, so these are just the diagnostic plots, so not much news here, right? It's very much the same that you're already familiar with from regression, right? Except for so the fitted, so here fitted values are of course for the 3 groups only, and then they should be like rough, so evenly distributed around this 0 horizontal line. So you can of course also do the QQ plots to check whether the residuals are normally distributed, which looks pretty good here, right? We have a few deviations here in the tail, so these are more extreme than, so they deviate more than would be expected from a normal distribution, but the scale is not, it's quite low, so that's all good. So it looks good, no problems here. So you also have the scale location plot, which also indicates here that there are no huge problems. And then the so the leverage versus standardized residuals plot is a little bit different in if you have only a one-way ANOVA, and so in this case, basically you're, instead of leverage, and if you have a balanced design, because usually the leverage is constant if your design is balanced. So in this case, you just have your factor level combinations on the x-axis, and then you standardize residuals on the y-axis. So that's just a little bit different than in regression, right? So leverage is only non-constant if you have unbalanced designs. All right. So very quickly, so the last few slides here. So about assumptions and violation of assumption when it comes to ANOVA. So you will often read things like ANOVA is robust to violation of assumptions. Yeah, so don't worry about the assumptions because ANOVA is really robust. Well, is it? It depends. So it's only robust if the group sizes are equal. So if you have a balanced design, and then it's moderately robust to violations of normality and homogeneity of variance. Again, so the same that we said for regression. So be cautious if you have extremely skewed or heavy tail distributions, right? If you have like an extreme skew or super heavy tails, I would rather be on the safe side, right? I would not rely on the fact that ANOVA is robust. And so, and when we say ANOVA is robust, it also means that your sample sizes have to be sufficiently large, which they're often not, especially not in neuroscience, right? So the more important it is to be really, really careful here, and maybe rather use a robust methods, which I will talk about in the remaining couple of minutes. Or at least if your homogeneity of variance assumption is violated, the Welch test is a Welch test instead of the regular F ratio, right? In general, so the normality assumption is less critical than the homogeneity of variance, but again, so you have to take that as a grain of salt. And then, of course, the violation of error independence is always a serious issue, but not only, there's no way, I mean, we have been saying that over the semester so many times, right? You cannot account for that unless you have something, and unless you have some time series model, right? So then you're explicitly modeling that, and you know there's like a what the temporal trend is or how your data are ordered, but otherwise you cannot really make up for that, right? So it's just a real problem, and in many cases you won't know. Okay, so what to do when assumptions are violated? So there are a bunch of options, right? So if you have non-homogeneous, if you have heterogeneous variances, then you can simply use Welch's adjusted F, right? So done deal, everything is good. You could also transform the data. If your data is non-normal, you can transform your data, but also that comes with problems in many cases, and it might not correct the issues that you're having, right? So because transforming the data changes the interpretation of the coefficients. So that might not always be the best thing to do. You can also use a non-parametric equivalent to the ANOVA. So for one-way ANOVA, that is a Kruskal-Wallis test. Which is basically based on ranks, yeah, like all the other. We talked about non-parametric correlation coefficients, and so in general, so there are so many tests that are called non-parametric are based on ranks, right? So that's why they get rid of any problems that have to do with non-normality, with heterogeneous variances. If you have outliers, if you have like any other issues with your data. Yeah. So you can also use robust ANOVA, so can also deal with outliers and violation of the other two assumptions. And you can use our very beloved resampling methods. You can bootstrap or use permutation analysis for your to generate your F distribution. And so in case you want to deal with violations of normality or homogeneity of variance problems. So again, so the resampling does not help with extreme outliers. Yeah? So that is something that you have to use a robust ANOVA for, ideally, even the non-parametric test, right? Remember that from the correlation classes, so the non-parametric tests are also, they can do only so much, right? So if you have extreme issues there, then you may want to use robust ANOVA instead. Okay, and then just to give you a very brief overview. So, right, I mentioned that, so the rank, basically the rank-based ANOVA is called the Kruskal-Wallis or Kruskal-Wallis test. And so you basically, you convert all your data to ranks, right? So instead of the actual measures on your dependent variable, and you order your scores from the lowest to the highest. And then these resulting ranks are added up for each group, right? And then you can calculate a test statistic. It's called H, according to this formula, right? So it's basically only based, all you have to know is the sum of the ranks in each group, your total sample size, and so how many subjects, observations you have in each group. And then this H statistic here is chi-squared distributed with a k-1 degrees of freedom, right? So it's also implemented in R. So it's a function that's called Kruskal.test. And in order, so that's basically to run the ANOVA equivalent. And then in order to conduct post hoc tests, you would do Wilkinson rank sum tests, which are the non-parametric version of an independent samples t-test, right? So be sure that you use those for So that you use those for balanced designs only, right? If you have an unbalanced design, that might be problematic, right? So in that case, things are getting a bit more difficult, and I would have to, I'm honest, so if you have an unbalanced design for non-parametric ANOVA, I would have to read a little bit myself how robust they are. In that case, I would assume it's not a big deal, but I cannot tell you for sure. Okay, then we can always bootstrap our ANOVA, right? So the same principle as usual. So we take our sample, our entire sample, right? We repeatedly draw new samples of size n. So n is the entire sample size, right? So let's say we have 20 subjects in each group. Yeah, so 3 groups, and our sample size is 60. So if we draw repeatedly new samples of size 60 and with replacement, right? And then, so that's the first step. So we randomly sample from our sample, and then each element is randomly assigned to one of our groups, right? According to original cell sizes. So if you had like an original design, if you had 20, 20, 20 in all groups, then it would randomly assign 20 resampled values to the first group, 20 to the second, 20 to the third. If you had like 15, 18, 24, then we would assign 15 to group 1, 18 to group 2, and 24 to group 3. And then we calculate the F statistic for each new sample, right? So we're drawing this random sample 60, so we're assigning them, then we are calculating the F statistic, and thereby we are generating our sampling distribution. Yeah, and then for each iteration, we determine whether the bootstrap F ratio is larger than the F ratio for the original sample or not. And then the p-value of our F statistic or F ratio is just a count of the the bootstrap F ratio that is larger than our original F ratio divided by the total number of draws. So how many iterations we go over, right? If we draw 10,000 samples, then we divide the number of times so our observed F ratio is larger than the original one, and that is our p-value, right? So for our observed statistic. So you have an R package that's called EasyBoot that allows you to do the to bootstrap ANOVA. So if you want to do post-hoc tests, you have to implement them yourself using boot, right? So you just have to write a small function again. So depending on what test you're using, I will try to include an additional example in our Markdown file. It's not in the tutorials that I have posted so far, just for those of you who are interested. Okay, and then permutation test, exactly same logic. The only thing is that we are that we are resampling without replacement. That means we are using that exact same sample of just my example 60 participants. And so we just basically over and over, we randomly assign the participants to the, or these observations, right, subjects to the groups, to our conditions, and then we calculate the F ratios for each, right, random assignment. And so the other, all other steps are identical. And so there in R has a package that's called COIN, and that provides a wide range of permutation tests, including the one-way test to compare some multiple means, so the one-way ANOVA equivalent, also the factorial ANOVA equivalent, and also the Kruskal-Wallis equivalent so that might be an answer to the question that I just asked. If you have an unbalanced design, so then I would use a permutation test or a bootstrap of the Kruskal-Wallis test. Here's your answer. Okay. All right, and then sorry for going over tonight. So that is my last slide. So you can also run as the ANOVA using robust estimators, and that is in the package that we already talked about for robust regressions, the WSR2 package. So in there are robust ANOVA methods that are based on trimmed means, right? Or we're taking off the highest, say, 5%, lowest 5% of a distribution, or 10%, whatever 1%, what you consider appropriate on M estimators or both. And so both of them can be combined with Bootstrap, right? So within that package. And so the robust version of your one-way ANOVA would be is implemented in the T1-way function in the WSR2 package. And so it also uses a generalization of the Welch method, right? So generally uses a generalization of Welch's method, WOP. So that's what makes it robust. And it also allows you to calculate post-hoc tests, right? So that's part of the package. So there's an extra function that you can define as an argument within your robust one-way ANOVA routine. And so it also has an interesting option that is called quantile ANOVA, which tests the hypothesis that J-independent groups have equal quantiles, right? And the default is they have equal medians rather than equal means, right? So, and that can be used in presence of outliers and other severe violations of the general assumption. So it's an interesting alternative, right? So it's quantile based and not mean based. So again, similar ideas, we had that. So other methods are using the same idea when we were talking about robust regression. And so I generally recommend to check out the WSR2 package. There's many robust methods, not only for ANOVA and for regression. There's a ton in there, and it's really cool. All right, so that's what I wanted to talk about today. Yeah, again, sorry for running over. So tomorrow we will continue with, so it's a two-way ANOVA as an example for factorial ANOVA, so with more than one factor, including interactions, and repeated measures ANOVA. Yeah, all right. Any questions, comments, remarks?
I just wanted to confirm that when you say that the design has to be balanced, like, are we saying that they have to be exactly equal, or just like,
Yeah.
so even if one group has one more participant, does that already throw everything off?
And that it's as usual. So I mean, the more unbalanced the worse. If you have like, if you're missing one participant in one group, it's probably not a big deal. But there's not like right, it's all arbitrary. I mean, it's the more unbalanced the worse. But yeah, so that it's not that you can. I mean, every threshold would be arbitrary. I mean, what I would do is, and also depends on your sample size. If you have 100 participants, so if you have 100 subjects in each group, and if you have 99 in one and 100 in all others, nobody cares. If we have 5 subjects in each group, then it matters a big deal, right? So, and with 5 subjects, I wouldn't run a parametric ANOVA anyway. So then we're gonna always do a non-parametric test, right? So if you have such a small sample size.
Yeah, that makes sense.
Right? So that means, and if you ever wonder, well, okay, I'm missing maybe 3 in that group, and so then do both. Always gives you like it gives you a lot of reassurance if the results are identical, and then you're on the safe side. So that's what I would do. So run the parametrics, the traditional ANOVA, and then run a robust method.
Okay, thank you.
All right. Anything else?
I was also confused about the definition of orthogonal. Does orthogonal in this case just refer to whether they're independent or not?
Yeah, independent and orthogonal is not, so independent is a little bit more involved. So orthogonal is more a geometric interpretation. So you can interpret it as non-correlated. Or if you really want to use a purely geometric interpretation, then orthogonal means that we have these vectors. So that just the numbers, and they are really orthogonal. They're in a 90-degree angle if you would plot them. So, but it is a form of independence, and has to do particularly with linear independence, but it's not quite as straightforward. So, but again, so there's nothing inherently wrong with non-orthogonal contrast. You just have to be aware. So non-orthogonal contrasts are not, it's that they are dependent. But the other way, it's not necessarily true, right? So when you know that something is non-orthogonal, then you know for sure they're also not independent.
Okay, got it.
But right, so there's this clear geometric interpretation. So what orthogonal, that's why it's also called orthogonal, right? And you can, if you remember, it means independent. So basically orthogonal means independent, it's fine. So it's right. So we are not statisticians, and for our purposes, it's okay. We just have to keep in mind that our comparisons are not independent. We are retesting the same, basically. They are linearly, so they are linearly dependent on each other. So we're basically making comparisons. We're reusing the same chunk of variation, and so that means that has important implications also for especially for the type 1 error rate, right? So that is in many situations can be further inflated, right? Or it depends on what the data look like. So you can either have, it can become overly conservative. So you can actually have so you can overestimate so the error that you're making, or it can become too liberal. Always depends on your data structure. So it can err in both directions, but you don't know how, because it depends on what's in there. I hope that makes some sense.
I guess overall you answered my question.
Okay. Right. Yeah. And if you want to know about the final or so, then I'm happy to answer questions. As I said, it will be very similar to, and not in terms of topics, but so the format will be very similar to the midterm, and it will focus on regression and ANOVA.
So it won't be cumulative because I saw in the other email that it was everything from the beginning of the semester.
Oh,
I'm
yes,
probably
right.
misled that.
Sorry. I said, yeah, I don't want you to.
Yeah, I was about to
thank
read
you.
all this, Dr.
Thank
Unger.
Thank you for mentioning that. Yeah, so that is correct. Thanks, Kimberly. So what I said is the emphasis will be on regression and ANOVA, but
Okay.
I don't want you to forget everything else. And it might be that there is something required from earlier in the semester, right? And I don't want you to say, well, Dr. Unger said there's only regression and ANOVA in this final, and I'm really upset now because there was a question about, I don't know, sampling methods or some question implied that. So that is very possible, right? So that you have like that a certain sub aspect of a question relates to something that we talked about earlier. So that
Okay.
yeah, so that
Makes
is
sense.
correlation, right? Things like that. Or
Okay.
even earlier in the semester, and I'm asking about sampling distributions, right? And that's also important, right? Because when we're doing bootstrapping, so you have to understand what sampling distribution is. I always want you to keep the dots connected and not, I don't want it to encourage you to forget everything else. And it might be important, but it won't be an exam only on the first half of the semester.
Gotcha.
All right.
So it'll be like a sub question, like A, B, C. Yeah, I see what you mean.
Yeah. And also, if you have any questions, I'm happy. So once I have graded the 2 assignments, I'm happy to give you like an update on where you're standing roughly. I mean, it's a bit difficult because there's still the final, right? And then there's one more assignment. But if you maybe you can let me know if you want to know what your current grade would be. So after you got the 2 outstanding grades, so then just shoot me an email and I can give you an estimate. Yeah, if you're interested in that. All right. Okay. Then thank you. Sorry for not giving you any time. Sorry for meeting. So I'll try my best to stop a little bit earlier tomorrow, that you have a few minutes to discuss the last assignment. Okay. All right.
Bye.
Good night.
Night.
Thank you.